And we are back in part 2 of the lecture. So now we are going to use the results of part 1, improving the first proposition of Archimedes that deals with the area of a circle. So proposition 1 says the following. Proposition 1 says the following, that the area of any circle is equal to area of a right triangle whose one side equals the radius of the circle and the other equals the circumference of the circle. Okay, we shall start with the proof. So we shall denote by r the radius of the circle and by c the circumference of the circle. All right, so here's what we want. Let's say that we have some circle, any given circle, okay, so the let's say the radius of the circle is r. So this is the radius r, and the circle is of circumference c. So let's say that we have the a right triangle whose one side is of length r and the other side is of length c. Okay, so this is the length r and this side is of length c, and we're making the distinction that this is actually a right triangle. Okay, so A would be the area of the, so A is the area of the circle, we'll denote that, and T will be the area of the triangle. Okay, so we must show that area A is exactly the same as area T. Okay, the way Archimedes went about it is by reducing this in all possible cases. So here we have two areas. The possibilities are three. Either one area, either A is less than T or T is less than A, and if none of these cases is a possibility, then A must be equal to T. So this is how we're going to proceed with this. Okay, first of all, note that T is what? T is equal to 1/2 R times C. And we know we want to find the area of A. We don't know what that is, but the claim is that it is exactly the same as the area T. Okay, So we are going to consider case 1. So case 1, we suppose that area A is in fact greater than area T. So let's assume for the moment that the area of the circle is actually greater than the area of this triangle. So if we say that, then the quantity A minus T must certainly be some positive quantity, some positive number. By the previous preliminary, what can we say? We know by the previous preliminary that we can inscribe a regular polygon inside the circle. So let me write this. We know from preliminary result that we can inscribe a regular polygon within the circle. We can inscribe a regular polygon within the circle. Whose area differs from the area of the circle, whose area differs from the area of the circle, by what? In the first page I said that, or the first part I said that given any circle, I can inscribe a regular polygon inside it such that the difference between area of the circle and area of the polygon is as small as I like. So how small do I want it in this case? I'm given this circle. I surely can inscribe a regular polygon inside it, and I can make sure that the difference between area of the polygon and area of the circle is actually smaller than this pre-assigned number A minus T. A minus T, it is some positive quantity. So, and it's assumed, or it's given to me. So that means I can make sure that the difference between the inscribed one and the circle, the difference in area, is less than this particular quantity or this particular number. Okay, so circle is less than my pre-assigned less than amount A minus T. Okay, so let's transfer this to some basic inequalities. So with other words, I'm saying the following, that area of the circle that I need to find out what it is, minus the area of some polygon that I will inscribe within the circle, that difference, the green really from the previous page, it is less than A minus T, which I said it is some positive amount. So in this inequality, I'm going to add and subtract from both sides. Well, not add, but just add to both sides. I'm going to add the following quantity. I'm going to add area of the polygon plus area of the triangle minus area of the circle. Whatever this is, certainly some amount. Area of the polygon exists. It is an amount. Area of the triangle, I know that it is equal to this. And area of the circle, it is again an amount that I want to determine. Nonetheless, this is some quantity. So all I'm going to do is add to both sides of this inequality this amount. Okay, so let's see what I get. I have area minus area of the polygon. I'm adding this plus area of the polygon, the very same polygon, plus T minus A minus area did I make a mistake? Yeah, no, no, I'm fine. This is less than, this is less than A. Let me make sure. Yeah, this is less than A minus T plus area of the polygon plus T minus area of the circle. Okay, so this and this cancel, this and this cancel, this and this cancel, this and this cancel. So what I'm left is what? Is the fact that area of the triangle is less than the area of the polygon. Less than the area of the polygon. Okay. Well, what would be the area of that polygon? I know what an area of a polygon is from theorem on the first part. Area of T is half R times C, I'm saying, is less than area of the polygon is 1 times the height, whatever the height of the inscribed polygon here is, times Q, and Q is the perimeter of the inscribed polygon. Again, refer to the picture on part 1. Okay. This, however, is a contradiction. Let's see why. But this is a contradiction. Yeah, okay. Well, let's see why. Now, let me bring the other page. The other page here for a second, so you'll see. C, first of all, is the circumference of the circle. We do have an inscribed polygon, so C cannot be smaller than Q. Okay, that's one of the reasons. So C is greater than Q since the polygon is inscribed in the circle. Since polygon is inscribed, so its perimeter lies within the circle, so the perimeter of the circle has to be larger than the perimeter of the polygon. So C here cannot be less than Q is inscribed. Okay. Also note the following. R is actually greater than H. Why R would be greater than H? Well, I'm just bringing this up. Imagine a circle outside this polygon. This is the area polygon. This would be the area, not the area, but this is the height of the polygon, and this would be the radius of the circle. So here R cannot be possibly less than the H in the case when the circle is outside this polygon. That's why. Again, for the same reason, R is greater than H. So this cannot possibly happen. Hence, A cannot be greater than T. So this supposed case is an impossibility. Okay, now we consider the other case, case 2. Let's consider the case when area A is in fact less than T. Let's see what happens when A is less than T. If A is less than T, then a minus t is greater than 0. I'm sorry, what am I saying? T minus a. T minus a. Okay. T minus a is a positive number. So what does this represent? If this is the case, t minus a represents what? Will represent the excess in the case when the polygon is circumscribed, is outside the circle but around the circle. So if this is the case, t minus a represents the excess area of the well, that too, but also of the triangle over the circle. Of the triangle over the circle. Okay. This actually doesn't represent the excess area between the circle and the circumscribed polygon. This is your pre-assigned small number that you are going to compare with that excess in the case of circumscribed polygon outside the circle. Okay, so what do we know? We know that we can circumscribe about the circle a polygon, a regular polygon whose area exceeds the circle's area by this pre-assigned amount, t minus a. Not by that, but by less than t minus a. So we assuming that a is less than t, that means that t minus a is a positive number. Well, a positive amount. So if we have a circle, we know that we can always circumscribe some regular polygon around it, like in here. Given a circle, we can circumscribe a regular polygon about it, and we can make sure that this green area here, that's what we're saying, it is smaller than this amount. This is my pre-assigned amount. So it is possible to make sure that this green hair, this area, this excess here, green excess here, is certainly less than my pre-assigned amount of t minus a. Okay. So, with other words, we're saying the following. Area of the polygon minus the area of the circle, because again the polygon would be outside the circle, and this indicates the green area I just showed you. It is less than t minus a. This is an inequality, and I can add and subtract from an inequality to both sides of inequality the same amount at the same time. So I'm going to add here, a to both sides. So let's see what I get. I have area of the polygon minus area that I had before plus a less than t minus a plus a. So plus a minus a plus a minus a cancel. And we are saying that area of the polygon is less than the area of the triangle. So what is the area of the polygon? From before we know that area of the polygon is 1h times q, where q is the perimeter of the polygon. And we're saying that this is less than the area of t. Area of t is 1 over 2 times r times c. So, but this is also a contradiction. Let's see why. This is also a contradiction. Okay, again, why? Okay, first of all, the polygon in question is outside the circle. So Q actually is larger than C. So since this is true, well, we have a contradiction because Q is larger than C. And what else? And R is in fact exactly as H in this case. So if you have, let me bring the picture again. If you were to draw, if you were to actually inscribe a circle here, much like here, this H would be exactly the same as the radius. Would be exactly the same as the radius of the circle, because the circle would pass here, right? So if you inscribe the circle, the H would be also the same as the radius. So R is equal to H, because polygon is circumscribed. About the circle. And that's why this is true. So it follows that this also is an impossibility. Area A cannot possibly be less than area T. So what we have left, A cannot be greater than T, A cannot be less than T, then A must be equal to T. Finally, we deduce that A must be equal to T, and that is the end of the proof. Now, a couple of comments here. We just said that we just talked about the circumference of the circle being related to pi. You might say, well, since you're showing that area of the circle is the same as area of this triangle, then aren't we done with squaring the circle or making sure that the circle is quadruple because the triangle is quadruple? Well, no, not in this case. Under no circumstances here is Archimedes interested, or he is showing the following, that you actually can construct this length C. It is one thing to be able to construct just by using compass and straight edge this length R, but so you can transfer this length from here to here, but it's another thing actually making sure that this length of this side is as long as the circumference of the circle. So he offers absolutely no proof, or he doesn't claim that you can actually construct easily this length C. And also the point of this proof is surely not to show that square, not the square, but the triangle is not the triangle. What am I saying? The square, the circle is quadruple. He's not showing that at all. The point of this proof is not that at all. It is simply just finding the area of the circle. Okay, so we are showing that we just showed here that area of the circle is the same as the area of the triangle. Okay, remember from part 1, I'm just going to continue. Okay. So, lecture 6, page 3, part 2. Bear with me for a moment. Marking my borders. So let's get back now to the modern formula for the area of a circle and the relation between these two constants that we mentioned in the beginning. So we said from the first part that circumference of a circle is equal to the number pi. Pi was the ratio of c over d, remember? So c is equal to pi over d times d, or 2 pi r, as we know the formula for the circumference of the circle to be. So we just showed that area of the circle is the same as the area of the triangle, but the area of the triangle is half r times the length c. So the length c from this formula is 2 pi r, so we have half times 2 pi r, or what we know the area to be simply pi r squared. I have this r here. Okay, pi r squared. Okay, Archimedes proved the following. So now we want to see what is the connection between this constant pi and that constant k that we mentioned in the first part. So Archimedes proved that, I'm not going to give the proof here, but he proved that if we let one circle, with area, let's call it A1, radius R1, and diameter D1, and another circle and another one with area 2, radius 2, and diameter 2, then we have the following. Area 1, which we just proved to be pi r1 squared, it is equal to, pi stays where it is, r1 squared is nothing other than d1 over 2 squared, or is the same as pi times d1 squared over 4. And the same can be said for the other circle. So area 2 is equal to pi r2 squared equals to pi d2 over 2 squared, or pi d2 squared over 4. Okay. Hence area 1 over area 2, if you put this together, would be pi times d1 squared over 4 over pi times d2 squared over 4. This is equal to simply d1 squared over d2 squared, which is actually what essentially Euclid proved. I believe we did mention that in the previous lectures. Euclid actually has proved that before. So looking back at the constant k, looking back at constant k in the beginning of the lecture, part 1, what do we have? We know that a is equal to k times d squared. By the way, this means that this ratio is actually a constant. But now we know that. We know what? We know that pi r squared is equal to area A, and I'm saying that area A from the first part is k times d squared, so that would be equal to k times d squared would be 2r squared, or this is equal to 4kr squared. This means, so this implies that this implies that 4k actually, it is equal to pi, or it implies further that k is equal to pi over 4. So that's the relation between the two constants, the constant k and pi that were mentioned in the beginning. A comment here, Archimedes of course throws in his proof the constant pi, but he just doesn't leave it at that. In fact, he is the first one to give an approximation of the constant pi. He actually proved in proposition 3 of the measure of a circle, the classic book that we're talking about now. He actually proved that, Archimedes proved also that pi is a number that is somewhere, well, certainly greater than 3 and 10/11, but less than 3 and 1/7. So if you are to actually compute these numbers, it turns out that this is just 3.140845 and continues less than pi, and pi less than 3.142857, and so on. So that's why a pi is taken to be approximately, or is rounded up to the first 2 decimal places, 1.4. Anyway, there is lots of literature on this fascinating number pi. Now to actually complete the reading of chapter 4, besides this great theorem, Archimedes also went on to write about the sphere and the cylinder, which is towards the end of this book of his, Measurement on a Circle, and it's very interesting read, and you should certainly read that on your own. Meanwhile, together with this lecture and the PDFs for this lecture, I will also post some announcement for the homeworks from the list of problems that are submitted on Blackboard. So that would be the end of lecture 6, and you'll hear from me again. So long, everyone.